Got a couple questions here. The first one, number 2, it says, using the emission spectra for hydrogen on the board and the table of wavelengths provided, estimate the wavelength of each of the spectral lines that you can see. Record your observed color and your estimated wavelength. So what happens is you've excited hydrogen, and then you've allowed a light to emit from the hydrogen, and then you split the light into different spectra, and you record the wavelength of each of those spectra. So here's my tube of hydrogen gas, alright, and I put an electrode on this side and an electrode on this side, and I pump electricity through the hydrogen gas, and then all of a sudden it shoots out light waves. You place a prism in front of those light waves, and what will happen is it will shoot out the various colors that the hydrogen had made. You can actually use a special device to find out exactly what the wavelength of each of those colors are, but for these purposes, just assume that we know what the wavelength of each color is. So you've seen, for example, a red light, and you know that red is 650 nanometers, or whatever the specific chart that you're given says it should be. Every source is going to give red, the color red, a different specific number. Red is actually a range of numbers of wavelengths. So you can have everything from a dark rouge all the way to a light red, a blood red. All these different specific colors of red have a different wavelength. I have populated this field right here with some of the average wavelengths listed in a physics textbook for each color. And so that basically takes care of problem number 2. We have seen the colors that come out of hydrogen, and we have estimated their wavelengths. Now there is a specific problem with this color right here, but we'll talk about that in a minute. Now question number 3 says, using Bohr's equation for energy of an electron, calculate the wavelengths of the first 4 lines in the Balmer series. So what is the Balmer series, you ask? Well, the question tells us. The Balmer series is a series of spectral emission lines from the hydrogen atoms that are observed in the visible range of the electromagnetic spectrum. Each of these lines results from electron transition from higher energy levels, greater than 2, down to the second energy level. Record the results and make sure to show your work for the transition from n equals 3 to n equals 2. Okay, I'm going to explain this question a little bit, but first I'm going to take a look at the 4th question. The 4th question says, identify which electron transition from n equals question mark to n equals 2 is responsible for each of the lines observed. So we're basically supposed to populate this field. So from n equals, let's just assume that this is n equals 3. We don't know that yet. So from the 3rd energy level, if electron drops down to the 2nd energy level, what wavelength of light is going to be observed? 654 nanometers is actually what's observed. And so that would probably be the red light that we're seeing. And we'll go ahead and I'll show you how to do that. But first I'm going to go back and I'm going to explain all the ideas that are involved in this question, in all of these questions. So you have your hydrogen atom, this is the nucleus, and then you have the electron. So hydrogen has 1 proton, 1 electron, and that electron resides in an energy level of n equals 1. So n is the energy level of an electron. And the simple model for this is the solar eclipse model. So we'll say that the electron can orbit the nucleus in very specific orbits. This isn't exactly true, but this was what Bohr thought, and so this was Bohr's model. So Bohr said there's an electron, whenever this energy level, this first energy level, n equals 1 gets filled up, then atoms start putting electrons in the second energy level. And whenever the second energy level gets filled up, they start putting electrons in the 3rd energy level, and so on and so forth. But then Bohr said, if this electron in the second energy level has energy added to it, so we're going to add electrical energy as we did, if it gets energy added to it, it can't jump from here to here, for example, because it can't reside there, but it can jump a discrete unit to here. It can jump an exact discrete unit, so it can move from this point to this point and nowhere in between. Whenever that energy is added, it jumps up here, then it immediately falls back down. It doesn't fall down to any of these spots in between, but it falls directly back down to the lowest possible energy level, or the next lowest energy level for the energy that it has. When it drops down to that energy level, it will emit some energy, and that energy is seen as light. So that's kind of modeled over here, and we can say that this is called the Balmer series, and I'll explain Balmer series here in a second. But the Balmer series, if if an electron drops from the 6th energy level down to the 2nd energy level, it will emit this much energy. If it drops from let's say the 5th energy level down to the 2nd energy level, it will emit that much energy. From the 3rd energy level down to the 2nd energy level, that much energy. And that energy is seen as a frequency, a specific frequency of light. And light, if you remember the frequency, the equation for frequency is equal to the speed of light, c, divided by the wavelength of light. I don't really want to go into explaining why that works, but it's fairly simple physics. Okay, let's talk about the Balmer series really quick. There are 3 series of spectral emissions that are associated with hydrogen. The first one was the Balmer series. There's also the Lyman and the Paschen series as well. So let's explain what the Balmer series is. There was a guy named Balmer, and he excited the hydrogen just like we had before. So here's my canister of hydrogen gas, and I'm going to put an electrode on this end and an electrode on this end, and I'm going to excite the gas, and then whenever it's excited, it's going to shoot out light. So whenever it shoots out that light, when you break it into a prism, you get your red, you also get your green, you also get probably like a blue and a violet. And I have to admit that I am red-green color deficient, so I don't know if I chose the exact right colors for all of these, but this is supposed to be red, green, blue, and violet. So Balmer observed all these colors, and he took the time to measure the wavelength of each of these colors. So he's like, okay, this red light's coming out. It's actually, the light is 656.3 nanometers, green light 486.17, blue light 434.1, and violet light 410.2 nanometers. So then Balmer created an equation to describe the wavelength coming out of hydrogen. And that equation looks something like this. So 1 over the wavelength of light is equal to some constant, r, times 1 over 2 squared minus 1 over n squared, where n is the number in the series. So for Balmer's series, n is equal to a number, the number of the wavelength. So the first wavelength, the second wavelength, the third wavelength. So n was a whole number, and it described which wavelength, what order the wavelength you were talking about. So if you're talking about the first wavelength, the second wavelength, the third wavelength, the fourth wavelength, these are what n is. So n is a whole number, 1, 2, 3, 4, and so on. Balmer didn't know why the equation worked. He just knew that he just made the equation fit the data. Then sometime later, somebody discovers, well, hydrogen doesn't just emit visible light, it also emits ultraviolet light and UV light. So Lyman, let me write this down, Lyman, he discovered that hydrogen can emit UV light, and he made an equation similar to Balmer's that would describe the UV light. So 1 over lambda is equal to some constant r sub h times 1 over 1 squared minus 1 over n squared. So you can see how it's similar. The visible light requires a 2 here. The ultraviolet light requires a 1. So what do these numbers mean? What are they telling us? Well, that takes us to Paschen. Paschen, P-A-S-C-H-E-N, he discovered that hydrogen also emits light in the infrared spectrum, and he created his equation. So 1 over lambda is equal to some constant r sub h times 1 over 3 squared minus 1 over n squared. And the interesting thing is that Bohr came along and he figured out what this 2 and this 1 and this 3 were talking about. So specifically, if an electron falls to the second energy level from any other level, that gives us the Balmer series. If it fell to the first energy level from any other level, that would give us the Lyman series. So this would be all UV light. And if it fell to the third level from any other level, this would give us the Paschen series, which gives us infrared light. So this was Bohr's third postulate. So Bohr had a lot of equations describing the energy level of an electron and how much energy it had. And so through his third postulate, we come up with basically this equation. So the final energy level, which the energy level that the electron lands in, so let's say it lands in the second energy level, so the final energy level in that case is equal to 2 for the Balmer series. And then here we have the initial energy level. From where did it fall? Well, if it fell from 4 to 2, then initial would be equal to 4. So this Bohr's postulate described the frequency, not the wavelength, but the frequency. So he's saying the initial energy minus the final energy divided by h bar was the frequency. So I don't want to describe what h bar is, but you can just think of the changes in energy, and that would describe the frequency that would be emitted. And so all of this, we can just ignore this because this is harder to calculate actually, and all of that would actually equal this equation right here. So how do we get from frequency to wavelength? Now, there's something called a Rydberg constant, and so the history, so I might have told the history just a little bit skewed. Rydberg actually came up with the initial easy equation for calculating all this, but then Bohr came along and explained what this Rydberg constant actually means. So the Rydberg constant, what we know now, is that it's equal to m sub e times k sub e squared times e to the fourth divided by 4 times pi times the speed of light times h bar to the third. Now you'll notice the speed of light shows up in this equation, and it's the only thing that's different from the Bohr third postulate equation. All of these variables end up, for hydrogen, they end up being a constant number, and so for hydrogen, the Rydberg constant is 1.097 times 10 to the 7th meters to the negative 1. So that's 10 to the 7th, and the units are meters to the negative 1, which is the same as 1 over meters. So this is just a little reminder of exponent rules. If we have a to the negative 2, that's equal to 1 over a squared, and so on. So whenever my unit is negative 1, then it's really 1 over that unit. Just a quick reminder. So like I just said, these numbers are not equal because this one contains the speed of light and this one doesn't. If we could find some way to divide this equation, this variable, by the speed of light, then we could replace it with the Rydberg constant. So we can do that by doing a substitution. So we know that this frequency is equal to the speed of light over lambda. So I replace the speed of light over lambda into that equation. And then when I do, I divide both sides by the speed of light, and I end up with 1 over lambda is equal to this. And specifically this times this. So whenever I substitute c over lambda in for the frequency, and then I solve for, or I don't solve, but I divide both sides by the speed of light, this is the equation that I end up with, which is the Rydberg equation. In other words, it's a simple form of Bohr's third postulate. So in the Rydberg equation, let me be clear, m in this case, m in Rydberg equation is equal to n final in the Bohr equation. So the final energy level, at what energy level are we stopping? So in the Balmer series, m is equal to 2. In the Lyman series, m is equal to 1. And in the Passion series, m is equal to 3. And then if you're thinking about this intuitively, let's say for the Balmer series, if m equals 2, then n must be greater than 2. An electron can only fall from a level greater than where it's falling to. So it can't fall upward, that's energy added. When energy is added, that means energy is absorbed and not transmitted, not emitted. So in order for light to be emitted, it has to lose energy, and that energy has to be released as light. So therefore, it has to fall from a higher energy level than where it's falling to. So in this case, we're going to say that n is always greater than m. And we're going to say that n and m are both whole numbers. Whole numbers that represent energy levels. And just a reminder, this Rydberg constant is supposed to say 10 to the 7th power. And the units are in 1 over meters. And so when your units are in 1 over meters, when you finally calculate wavelength, when we get finally to the point where you're calculating wavelength, your answer will be in meters, and you will want to convert to nanometers. And so we're not actually trying to solve for 1 over the wavelength, we're trying to solve for the wavelength. So in order to do that, there's 2 simple algebraic ways to solve. So you can flip both sides of the equation over, and you get lambda over 1, or just lambda, which is equal to lambda, is equal to 1 divided by r sub h times 1 over m squared minus 1 over n squared, and then you calculate it like that. The other way is you can remember that taking something to the negative 1 is the exact same as taking its inverse, and so you just put your caret sign and negative 1 in your calculator, and that will convert all of this into its inverse, which is this, and you can calculate the wavelength like that. Now remember, once you get your answer, convert to nanometers by multiplying by 10 to the 9th. 10 to the 9th power. So for example, if light is moving, example of light moving, so from n equals 3, and this should say electron, so electron moving, from n equals 3 to n equals 2, then we would put 2 as our m squared, so its final position, n equals 2, initial position is n equals 3, it's falling from 3 to 2, and so we plug the numbers in. We plug in our Rydberg constant for RH, we plug in 3 here, which is going to equal 1 over 9 minus 1 over 4, so 1 over 9 minus 1 over 4, and then we're going to multiply that by this number, so RH, and then we're going to take the whole thing to the negative 1 power, and that will equal our wavelength in meters. Remember that it's in meters, and remember to convert that to nanometers by multiplying by 10 to the 9th power. So from n equals 3 to n equals 2, which is the first number in the Balmer series, so the second number in the Balmer series would be from 4 to 2, then the third number would be from 5 to 2, and so on. So the first number in the Balmer series is a wavelength of 656.3 nanometers. And then you can continue that for all of the Balmer series. So this is the first in the Balmer series, second, So second, third, fourth, the fourth number in the Balmer series, where n equals 6. And so you can calculate the wavelength for each of those numbers in the Balmer series. So you have each of your numbers in the Balmer series. So this is the first number in the Balmer series. And I look down here and I see the closest number I have to 656 is 650. So I think the red light that I was looking at and I estimated at 650, I think that was actually 656. And then you continue. So the next number I saw was 486. Well, you know, there isn't the 510 is closer to 486 than it is to 570. It's probably closer to 475, but if you look at actually what each of these colors represent, so 656 is going to be red, 486 is going to be a blue-green / cayenne or cyan, however you want to say that. And then the rest of the colors that you see are going to be violet. So the next one is also going to be a violet, which would be the fourth number in the series. And so I don't know how you want to divide these up, whether you want to say that this goes into this column, into this cell, or what the case may be. But I'm just trying to put these together in a way that might make sense for this chart and for this homework problem. And so I just, this is the best way I can make it work for you. So with that in mind, let's go ahead and calculate percent error. Percent error is the absolute value of your estimated wavelength minus your calculated wavelength divided by the calculated wavelength. So we're saying, what's the difference in my estimation and calculation divided by my calculation. And then you can multiply that by 100%, and that will give you your percent error. So I'll take this line right here. I estimated it at 650, so I put 650 in here. I calculated at 656.34. When I take the absolute value of that, it's approximately 6.34. When I divide that by 656, I get 0.009. When I convert that to a percent, it's 0.9%. So I can throw that in there. There's my answer. And these are the answers I get for each of the values in the chart. And so you can, if you have, of course, different numbers than these, then you can also use those different numbers as well. As a caveat, I took these numbers from a standard chart. Your chart might be different, and if your chart is different, you may have to line up your calculated values differently than I did, and that will also give you different percent errors. For example, if your professor said yellow, the yellow he was looking at was really closer to 525 nanometers, then you will maybe you can shift all this stuff down. I don't know. I really can't see it, but that's possible. Anyhow, that's the Bohr and Balmer series, the Paschen and Lyman series. So I hope it helped you. Leave questions in the comments below.